guys, remember, I encourage you to ask questions. We are just 20 questions away from me doing a handstand. If all of you ask a question, I will do a handstand next lecture. Okay, so ask as many questions as you want. Let's begin our second half. So now let's actually try to describe some motion. Before we describe motion, let's try to just describe where we are. Just describe the location of something at a specific time. Have you guys been to downtown? Davis downtown? Oh good. So you should know that if you are in downtown, it's very easy for you to describe where you are to your friends. You can just say I'm at G and C Street, then your friend will immediately know that G Street is this is A, B, C, D, E, F, G, and then you go first, second, and third, and you know you are right there. Or you can just say B and second, and then your friend can easily follow. So if you have a street like Davis downtown, which is like making a grid line with horizontal and vertical, it's easy to describe location. Unfortunately, not all the street looks like that. And we don't have street at everywhere. So in order to describe the location, we have to make out our own grid line. Let's say we have a black point at here, a black particle, and there's a blue particle. It looks white, but it's blue because it is a P. And let's say there's a green particle over here, and there's a red particle over here. So what you're looking at is just some particle at a specific time, or we will say at a specific state. A state is not like California or Texas. A state in our class means a specific time instant. So let's say at 9:28 a.m., these particles are like this. Then we say this is a state. So to describe where the red particle is, we need to draw a grid line by ourselves because this is not Davis downtown. So we can do something like this. We just draw a horizontal exit and a vertical exit, just like the ABC street and 1, 2, 3, 4, 5, 6 street in downtown. But ABCD, there's only like 26 alphabets. We want to be more general. We want to go from all the way to minus far, very far to plus very far. So we use numbers for both of them. To distinguish them, we call the horizontal one X, the vertical one Y. I should have write something like here. Have you guys learned something like this before? Should I speed? I'm not going to speed. I'll go faster. All right, so I'll just put this grid line on this state. And right now, I put the black dot at the origin. You know what is origin? Origin is the point that is 0 for x and 0 for y. Good. So now I can draw the grid lines. Let's say the green particle is up here. I can count 1, 2, 3 along the x-axis and say the x position of the green particle is 3. Okay? And we can write it as a parenthesis. The first number is the x position. For the y position, we need to go down one line along the y-axis. When you go down, it's negative. So the y position of the green particle is -1. You can do the whole thing for the red particle here and the blue particle here. And it will look something like this. The blue particle has -2 and -2. The red one has 2 and 3. Okay? Now, this axis, this grid line, sometimes are called coordinate system. We are going to call it mostly frame. It's a frame. And for this one, especially, this is the black dot frame, because we put the origin at the black dot. It kind of represents what the black dot is seeing. The black dot sees that the red one is over here, the green one is down here, blue one is down here. So the black dot frame kind of represents the point of view of black dot. Okay? When we say something is frame, it means that the frame always has that thing at the origin. So the thing is that the state by itself is like this. The state itself is independent of frame. It has nothing to do with the frame. Where should I write it? The state itself is independent of the frame. We can choose any frame to describe this state. There's no specific reason that we should choose the black dot frame. And like we can choose the red dot frame, the green dot frame, and the blue dot frame. There's no good or bad or right or wrong. It's just something we impose to help us describe the location. So instead of black dot frame, I can put my coordinate system on the green dot. So right now I'm looking at the green dot frame. In the green dot frame here, the red dot should be over here. In the green dot frame, you need to go left by one grid line to go to red dot. So in the green dot frame, the red dot has -1 as the x coordinate. Okay? So you see the x and y position is different in different frames. The x and y position depends on which frame you are using to describe the x and y position. Now, this frame dependence has a strong relation with the requirement for physics law. In the beginning, we said physics law should work the same for anyone, anywhere, at any time. Now, different dots is just like different plates in that sentence. If I'm looking at the state in the green dot frame, it is how physics work at the green dot frame. And it should be independent of which frame I'm using, because physics law should work the same for any dots, and no matter where you put your origin, the physics law should be the same. So instead of saying a whole bunch of things, the requirement for physics law is that it should be frame independent. Physics law should be the same no matter which frame you are choosing to describe the motion of the particles. Does that make sense? Good. So now, we just learned that we can describe the location with x and y position. But x and y position depends on which frame you are using. Therefore, we cannot come up with a physics law just with x and y position, because it's not going to be frame independent. If you say, all right, according to my law, the x position should be this, the other guy will just say, no, the x position is not that according to my frame, so you know it's not going to work. Therefore, we need to go farther. So let me spoil a little bit of the goal for this week. The goal for this week is to figure out something called acceleration, x and y acceleration. Right now we're looking at x and y position. The goal for today is to know how to go from x and y position to x and y velocity. There's 2 because there's x and y, they are totally different things. And on Thursday, we will go to x and y acceleration. Acceleration, x and y acceleration are defined in terms of x and y velocity, so that's why we need to do x and y velocity first. And the reason that we need to go through all the effort is because x and y acceleration will be the same in all the frames. It is a frame independent quantity. So you will see that Newton's came up with F equals ma. The a is the x and y acceleration. And the reason he do that is because physics law should work the same in all the frames. So you need to describe physics law in terms of the thing that is frame dependent. That is acceleration. And this is why we are going there. Okay? So let's see some motion. This is a tree, a boy, a baseball, and a unicorn doing whatever they're doing. The left-hand side is how the motion looks like in the tree's frame. You can see the tree is always at the origin. It represents what a tree sees that's happening. The right-hand side is the boy's frame. It represents what the boy thinks is happening. In the tree's frame, the boy is running, and the boy is flying to the right. And in the boy's frame, the tree is moving, because when the boy is running, you will see the tree approaching him. So in the boy's point of view, the tree is moving. And if you look at the ball, it's just going straight up and then straight down. When in the tree's frame, the ball is flying to the right. So you see the motion in different frames different. But what we're doing right now is just describing the location of the object for many different states. In the 5 minutes ago, we were just describing the location of the dot in one specific frame, one specific time. To describe this motion, we just do the same thing for all the time. We just do the same thing for t equals 0, 0.5, 1, 1.5, and then we're describing motion. So the key is to just describe the location at all the time. It is kind of hard to just keep looking at this animation, so let's look at the trajectory. This is the same thing, but I just draw the position of the object on the same graph. There's a lot of image because I know what I'm drawing. I can just pause at smaller and smaller time instance. Previously, I have 0.5, 1, 1.5, and 2, so there should be only 5. But so even though here is only 5, but I know what I'm drawing, so I can just cut it into a smaller time instant and draw more detail of this motion. Okay? So you see in the tree's frame, the ball is moving, the ball is going to the right, the unicorn jumps to the left and then jumps back.